Hello everyone. Today we will be presenting our TEM project on the field vein shear test prepared by me and Ali Kılınç. This test is a commonly used method in geotechnical engineering to determine the undrained shear strength of soft saturated soils. The field vein shear test is designed for saturated clays with undrained shear strength values ranging from 0 to 200 kilonewtons per square meter. It is also suitable for silts, organic soils, and wet slides. However, it cannot be used in highly permeable soils like sand and gravels because partial drainage may occur during the test. This test method gives especially reliable results in soft or sensitive marine deposits. There are several standards that define how the field vein shear test should be performed, and some of the most widely used ones are ASTM D2573, BS 1377, Part 9, 1990, AS 12.8 9.6.4, and ISO 22476-2. Each standard provides slightly different procedures, but the fundamental approach is the same. The vein apparatus consists of four rectangular blades mounted at right angles, connect to a vertical rod. It is inserted into the ground to a desired depth, and torque is applied from the surface at a constant rate until failure occurs. At that point, the undrained shear strength is calculated based on the limit equilibrium theory. After insertion, when the vein reaches the target depth, torque is applied to rotate the blades. The resistance from the soil helps determine its shear strength. A field vein shear test apparatus specially designed for this method is used in practice. According to ASTM D2573, the vein consists of four orthogonal steel blades fixed to a vertical shaft. The blades are typically made from nickel, chrome, or hardened steel alloys. Their tips can be flat or conical to minimize soil disturbance, and recommended dimensions such as the height to diameter ratio and blade thickness are shown in the table on the right. A typical HV-DV ratio is 2.0. The vein diameter, or DV, is selected based on the soil consistency. For soft soils, a larger vein, usually around 65 millimeters, and for stiffer clays, a smaller one, typically 35 to 50 millimeters. And when testing from the bottom of a borehole, the vein must fit within the casing. Several vein types, including inclined veins, are illustrated in the figure. Another important parameter is the area ratio, denoted as a VA. It is the ratio of the volume of displaced soil to the volume of the failure surface. To minimize soil disturbance, the area ratio should be below 12%. This can be achieved by reducing vein thickness and rod diameter. For tapered vein devices, the area ratio can be as low as 10%. The formula for this is given in the figure. Another factor is the parameter ratio, denoted as a AV. The relationship between parameter ratio and shear strength is shown in the adjacent graph. A zero parameter ratio, AV equals to 0, gives the true undisturbed shear strength. However, standard veins with 2 millimeter blade thickness result in a parameter ratio of 3.1%, which can cause 10 to 20% underestimation of strength. Now let's continue with the test procedure. Insertion of the vein shear device into the soil. In this step, we insert the vein into the soil to the desired test depth. Once inserted, torque is applied at a constant rate and the soil's resistance is recorded. The figure on the The figure on the slides show different insertion methods used in practice at the slide. And measurement of friction developed on the road. The adjacent figure illustrates different insertion methods of the field vane shear device into the soil, which result in the varying frictional effects. If the rod is not protected by a casing, as shown in the figure A, the friction between soil and rod must be measured separately. This is done using torque test with rods that have no vane blades at the end. These tests should be conducted at each site at various depths. In other methods, such as the one shown in the figure D, friction is negligible due to casing and isolation of the rod. After reaching the test depth, the test must begin within 5 minutes. Torque is applied at a rotation rate 0.1 degrees per second. The recommended range by ASTM D2573 is 0.05 to 0.2 degrees per second. The test usually lasts 2 to 5 minutes, but can take up to 20 minutes in soft glass. Peak torque is recorded, followed by a rapid remolding pace, which helps determine the remolded underrange shear strength, denoted as a CUR. According to ASTM D2573, the next test depth is chosen by the engineer, but it must be at least 50 to 75 centimeters below the previous one. Errors during the test can affect the results, and common sources of error and their impact on calculated underage shear strength are summarized in the table on the slide, as you can see. That concludes the first part of our presentation. From this point on, Ali Kılınç will continue with the remaining slides.
Hello friends, also I am Ali. In the remaining part of the presentation, I will talk about underrange shear strength, calculations, correction factor, OCR over consolidation ratio, and pre-consolidation ratio. Let's start with underrange shear strength calculations. In the field vane shear test, the applied torque creates both horizontal and vertical shear planes along the cylinder failure surface. The horizontal shear planes correspond to the top and bottom circular faces of the cylinder, while the vertical shear plane refers to the rectangular surface surrounding the cylinder. In underrange shear strength calculation using limit equilibrium theories, several assumptions are made. No drainage occurs during the test. The shear stress mobilized along the shear plane are uniform, and the soil surrounding the cylindrical shear surface is isotropic and homogeneous. However, the validity of these assumptions has been questioned for many years, and both numerical and experimental studies have been conducted to determine the stress distributions along the shear plane. Donald investigated the stress distributions along the shear planes using a three-dimensional finite element method. Later, Menzies and Merrifield conducted an experimental study on the same subject. Both studies yielded consistent results, and the shear stress distribution shown in figure 4.6 were obtained. Ford, who evaluated the results of these studies, proposed equation 4.3 for the stress distribution on the top and bottom circular shear planes. Here R is the distance from the center of the vane shear device, tau H, the shear stress at a distance R from the center, and tau MH, the maximum shear stress and the outer boundary of the cylinder, where R equals capital R equals dV divided by 2 on the horizontal shear plane. If the shear stress distribution on the horizontal when NV becomes zero, considering this boundary stress distribution for a vane shear device with the height HV and a radius R equals dV divided by 2, the moment equilibrium condition leads to the validity of equation 4.4. Here, TH is the component of the applied torque acting on the horizontal shear planes. By substituting the value of the tau h from equation 4.3 into equation 4.4 and performing the integration, equation 4.5 can be derived. Equation 4.5 proposed by Wirth provides the component of the applied torque on the top and bottom circular shear planes based on the stress distribution shown in figure 4.6. In general, it's commonly accepted that the shear stress are uniform along the vertical cylindrical surface. Under this condition, the vertical component of the applied torque, Tv, is 4.6. If the applied torque value is Tv, then it is the sum of the horizontal and vertical components 4.7. In the analysis, it is considered that the shear strength of the soil is mobilized under condition where the maximum shear stress occur, tau mh equals cuh, tau mv equals cuv, where the cuh is the undrained shear strength on the horizontal plane and cuv is the undrained shear strength on the vertical plane. If the soil isn't isotropic in terms of its strength, this characteristics is represented by the coefficient BV. When equation 4.5, 4.6, and 4.8 are substituted into equation 4.7, the general expression 4.9 shown on the side is obtained. This expression accounts for the anisotropic strain characteristics of the soil as well as the varying stress distribution conditions on the horizontal plane. In standard evaluation methods of the vane shear test, it is assumed that there is a uniform stress distribution on the horizontal shear plane NV equals 0 and isotropic strength characteristics PV equals 1. Additionally, standard vane dimensions are dV equals HV divided by 2. Under these conditions, the expressions can be written as equation 4.9, where CUV is the undrained shear strength and TBM is the maximum torque applied during the test. In the case of isotropic shear strength, and when MV plus 3 equals A is defined in equation 4.9, the expressions become 4.11. It has been emphasized that under the condition of uniform stress distribution and when the soil possesses anisotropic shear strength, equation 4.12 becomes valid. By using equation 4.12, when shear test with different HV dV ratios are conducted at closely spaced location and the test data are plotted according to coordinates defined in the charts shown in figure 4.7, the values of CUV and PV equals CUV divided by CUH can be determined. Let's say correction factor. The undrained shear strength value determined from the field vane test may differ from the actual value due to factors such as soil disturbance, anisotropic soil behavior, the strain rate applied during the test, and potential partial drainage. Pierre emphasized that the actual undrained stress shear strength determined by back analysis of slope values are lower than those obtained from vane shear test, and that the correction factor given in equation 4.13 should be applied. Here CU Saha The actual drained shear strength to be used in design, CUV, the undrained shear strength calculated from the field vane shear test, mu, the correction factor which depends on the plasticity index of the clay. The relationship between the correction factor derived from back analysis of slope failures by barium and the plasticity index is shown in figure 4.8. Over consolidation ratio, OCR, and pre-consolidation pressure. Main and Mitchell evaluated a comprehensive debates from 96 different sites covering soil index properties, consolidation, and vein shear tests, where the over consolidation ratio ranged between 1 and 40. Based on this evaluation, they proposed equation 4.14 to relate OCR to the undrained shear strength CUV obtained from the vein shear test. Alternatively, Main and Mitchell proposed equation 4.15 for estimating of OCR. Here, alpha FV is the correlation coefficient that needs to be determined for local soil conditions. Overconcentration ratio and pre-concentration ratio pressure'ın CUV and sigma V 0'nun OCR'a ilişkisi. Next please. As a preliminary approach, Main and Mitchell proposed the relation given in equation 4.16. Here. Thanks for listening. Thank you.